This introductory material in section 6.2 is mostly there to establish where the idea of having a series solution makes sense, or where you'd actually be able to get one. So the first thing is an ordinary point. Basically, it's one where you'd actually get a second order equation, right? Because if p of x0 is equal to 0, then you wouldn't have a second order equation there. Right? And that's what a singular point would be. But if you have an ordinary point, you would be able to figure out an interval or a neighborhood with a specified radius, where then inside that interval you would have no singular points and just ordinary points. And then in that situation, then y is going to be analytic. And so then we're basically good to go. And then that's really just the only situation we're going to be concerned with here. So if y is analytic in a neighborhood of an ordinary point x sub 0, then you can write y like this, right? So using a power series. And then if 0 is an ordinary point, this simplifies a little bit, right? Because then x sub 0 is going to be 0. So then these all get a little bit easier. The sum gets a little bit easier to write out. And then here's the key point, that you'd be able to write y like this. So a0 times y1 plus a1 times y2. The a0 and the a1 are arbitrary constants, and then the y1 and the y2 are going to be series. So that's, well, I guess not always. If it's a situation where you have to do it with a series solution, then they're both going to be series. If it's one where you happen to do it that way, but you didn't actually have to use a series, you could have done it a different way as well, then maybe one of those wouldn't end up actually being a series. Like sometimes you get that y1 is 1, but that's really just in situations where you didn't have to use a series solution. You just happen to do it like that. All right, so the general steps. I think this is actually the most important stuff on this page for what we're about to do. So if you can write y as a power series, you're probably also going to need y prime and y double prime, right? Because if it's a first order equation, you don't have to use series, so you probably wouldn't pick it because it's kind of long. But with a second order, you might need it. So probably going to be a second order situation. So the derivatives are just power rule derivatives, right? So, okay, we're going to need these, and they're always going to look like this. So at least that's nice. It's going to be consistent. So then what you end up doing is, after you substitute in, then you want to rewrite all the sums so the exponents match up. Then after the exponents match up, you want all the starting points of the sums to match up. Once you're there, you can combine the sums together. And then from there, knowing that the coefficient of each power of x will have to be equal to 0, that'll give you a way to get a recurrence formula for how to get the constant terms in terms of previous constant terms, right? There's the recurrence part. And then what you end up doing, and this is the long part actually, believe it or not, the series part is not the long part. It's what you do after you get the recurrence formula. It's long. Where then you end up expressing a2, a3, a4, and so forth in terms of a0 and a1. What usually happens if you're doing this with a second order equation is that all of the even ones end up kind of blocked off as one thing and the odd ones are another. Like you end up being able to rewrite a3 in terms of a1, then a5 in terms of a3, kind of like that. And then I guess a2 in terms of a0, and then a4 in terms of a2, and that kind of thing. And then you can usually rewrite those so they're all just in terms of a0 and a1, and then you would get expressions for y1 and y2, and then y1 and or y2 might be power series. Usually they end up being series, but like I said, sometimes you get lucky and maybe y1 is just 1 or something. You do see that once in a while. This first example, looking at it, you think, okay, yeah, this is one where we're not going to be using anything from chapter 4, right? I mean, like, look at these coefficients. They've got x's in them. So we're going to need something new. And this isn't a matrix situation either, right? It's just one single equation. So this is one where, yeah, we're basically forced into series. And, okay, Well, we know how to set up y prime, y double prime, because if y is just some general power series, we can take its derivative to get y prime, and then take its derivative to get y double prime. And then if we're going to sub into the differential equation, so then here's y double prime, this sum, then here's y prime, and then here's y. And then I have this one underlined because then what I'm going to do in the next line really just involves this. I'm going to break it into two pieces. So I'm going to write it as x squared times this sum minus 1 times this sum. And that's what this is right here. So these first two terms here, there's x squared times y double prime minus 1, I guess, times y double prime. And then the rest of this is just repeated from above. Next line, what I'm going to do is I'm going to take this one and I'm going to put the x squared inside the summation. So that's why that's underlined here. And what's happening down here is if you put the x squared in here, you have x to the power of n minus 2 plus 2, which is just n. So there's the x to the n, right? There's everything that comes before it. And then I can do the same thing with this one. I've got an x out front. If I put that in here, that would become the sum from n equals 1 to infinity of a sub n times n x to the n, right? Because now you have x to the n minus 1 times x to the first. So that's just x to the n. And let's see, then that one and that one are staying the same. All right. So then once we get to that point, we can try to match up the exponents. So I'm going to try to get them all with x to the n because this one is already x to the n, so is the third one, so is the fourth one. That way I only have to adjust one of the sums. That seems like the simplest thing to do. So with this sum, I need an x to the n on x to the n minus 2. That means I've got to go plus 2 on everything here that's being summed, and then I've got to go minus 2 on the starting point. So that's what happens here, right? I wanted x to the n, but along with that, I'm going to get a sub n plus 2, right? There's n being replaced by n plus 2. Same thing here, right? That's up 2, and then up 2 from there, right? n minus 1 to n plus 1, but then down 2 on the starting point of the summation. So from here it was n equals 2, here it's n equals 0. Okay? Well, now we've got the powers of x matched up. Then we have to match up the starting points. Starts at 2, 0, 1, and 0. So basically it's the latest starting point is the one you have to aim for. So here that's 2, because I can make this sum start at 2 if I just pull the first two terms off. Here I have to pull the first term off, and then here I have to pull the first two terms off. So that's what this is. When n equals 0, you would get a term in this one and a term in this one, but not in the first or third sums. So here I said, okay, if n is 0, you get the negation from right there of a sub 2 times 1 times x to the 0, but that's negative 2 a sub 2. And then down here, do the same thing. Sub in 0 for n, you're going to get minus 2 a sub 0 times x to the 0, but that's minus 2 a 0. All right. Then when n equals 1, we're going to get a term here, here, and here. So first one, I guess from the second sum, if you sub in 1 for n, you're going to end up with this, right? The negation of a sub 3 times 2 times x to the first power. That's negative 6 a sub 3 times x. Here, you could pull off that first term when n equals 1. That's going to be a sub 1 times x to the first. That's a sub 1 times x. And then here, pulling off the term where n equals 1, minus 2 times a sub 1 times x to the first, so minus 2 a sub 1x. Okay. Once you pull all that stuff off, so here are those 5 terms, right? So those 2 and then those 3, all out front, because then you can start all 4 of these sums at n equals 2. So then that's what I did here and just combined the 4 sums together. So you'd have n equals 2 to infinity, right? Starting point of n equals 2. And then we know that they have all got an x to the n in them, right? So there's that out there. And then the coefficient of x to the n, basically you just have to combine all 4 of these. So you have a sub n times n minus 1, that's the first one, minus what you get from the second one, a sub n plus 2 times n plus 2 times n plus 1. Then plus what you get from the third, which is a sub n times n, minus what you get from the fourth, minus 2a sub n. That's the coefficient of x to the n. That's equal to 0. I guess the edge of that 0 is chopped off, but that's a 0. Okay. Well, then what I did here was I sort of combined like terms out front. I said, okay, those first 2 are just constants. And then these 3 all have an x in them, so we can combine those together. right? So minus 6a3 minus a1 would be the coefficient of x there. And then I tried to combine terms here. Everything with an a sub n in it, I combined together and I said, okay, n squared minus n right there. And then down here you have an n minus 2. So there's the plus n minus 2. And then the only thing with an a sub n plus 2 in it is this term right here. All right, well then going a little bit farther, let's see, I guess here you could combine terms a little and say that's really just n squared minus 2. And that's what it looks like right there. But first we have the things in front of the sum, right? Because we have to get 0. And since x can vary, then like that thing in brackets has got to be 0. Minus 6a3 minus a1 has got to be 0. And then this constant's got to be 0. So I guess going left to right, the constant goes first. So minus 2a2 minus 2a0 has got to be 0. Well, then that would mean a2 has to be minus a0. Then this thing in parentheses has got to be a0. So I solve that for a3. So I guess solve it for the higher index. Then it would be equal to minus 1/6 a1. And then this whole thing in brackets is also equal to 0. So here's that with the simplification right there with the n squared minus 2. So again, you solve for the higher index. So you want to solve for a sub n plus 2, not for a sub n. If you solve for a sub n plus 2, you get this. That's the recurrence formula. Okay, good. Once you get there, I don't want to say it's downhill from there, but I would say that's probably the halfway point. I think that's reasonable. So the final answer should be of this form, right? Where it's a0 times something plus a1 times something, or a0y1 plus a1y2 to phrase it like it is on the first page. So this is what we're aiming for. We've got the recurrence formula, so we're going to have to use this to get it. So I said, all right, well, the first thing is what if n is 0, right? That's the first constant that we'd have to figure out. All right, well then, based on what's up here, if I just sub in, then that means a sub 2, right? Because n plus 2 is just going to be 2 if n is 0. It would be a0 times 0 squared minus 2, which is negative 2, over 2 times 1. Okay, well then that's just negative a0, but we knew this already, right? If we go up there, it's this. But this is almost functioning like a check. We know what we're supposed to get and we're getting it. So that's nice. Then if n equals 1, this one's also a check. Because then that's a3, right? Because 1 plus 2 is going to be 3. That's equal to a1 times 1 squared minus 2, but that's going to be a minus 1, divided by 6. So that's negative 1/6 a1, or negative a1 over 6. Oh, look, that's also what we're supposed to get. Okay, looks like we got the right recurrence formula if we're getting the stuff that we're supposed to get. After that, we're supposed to get a bunch of other terms. Let's see, so that's the first 4 that we've got right now, right? So we got a0, a1, a2, a3. We need a4, a5, a6, and a7. I did the even ones and then the odd ones just in case there was a pattern. I figured that would be the more prudent way of going about it. But if n equals 2, that'll give us a4, and then subbing into the recurrence formula, that's going to be a2 times 2 squared minus 2 over 4 times 3. And this is the part that gets a little bit odd, because you say, okay, that's a 2. Why am I not doing anything with this? Right, why don't I call this a 12 and then go, oh, well, this is going to be a2 over 6. The reason that I'm not doing it is, I guess for one thing, we want to be able to rewrite this in terms of a0, which, I mean, I guess even if you simplified here, you could still do that. But the other thing, and this is the important thing, if there's a pattern, it's going to be easier to see if you don't simplify. So I know that goes against everything that you get told, right? Where it's always, simplify, simplify, simplify as far as you can. But that actually goes against what you're trying to do here. You're better off just leaving things like this. Because then when I sub in a0, I know this is kind of a tough move to see like why you would do this. So, because we said, all right, well then a2 is negative a0, so I sub that in. But then why am I doing this? Like multiplying the top and the bottom by 2. It's so I can get that factorial. Because factorials show up an awful lot in series solutions. So if there's going to be a pattern, I would think it would involve the factorial. Right? That's very likely. So that's why I did it. But then I guess after that we can get n equals 4. That'll give us a6. And so then that should be a4 times 14 over 6 times 5. So then notice when I sub in for the A4, I leave the 6 times 5 alone. And then I said, okay, well, this is what A4 was when we had it right here. But then 6 times 5 times 4 factorial is 6 factorial. 14 times negative 4, I don't know if there's anything we can really do with that one. Right, that's not like an obvious pattern here to go from negative 1 to negative 4 to negative 56. So I guess for now, we're just going to kind of leave those that way, especially because we're only supposed to get the first few terms. This is one where we can leave them that way. Then the odd ones, if n is 3, we can get A5. So by subbing in, we end up here. So that's 7 times A3 over 5 times 4. And then A3 was negative A1 over 6. But 6 is 3 factorial. So, right, 6 times 5 times 4 would be the same as 5 times 4 times 3 times 2. Right, just to kind of rephrase that so it's more like a factorial. But then that's 5 factorial. All right. So then at least we're seeing some kind of pattern, right? A4 has got 4 factorial in the denominator. A6 has got 6 factorial. A5's got 5 factorial. A7 has got 7 factorial, right? Because if you rewrite A7 using the recurrence formula to A5 times 5 squared minus 2 over 7 times 6. So that's 7 times 6 when we're going to sub in here where we'd have that A5 is negative 7A1 over 5 factorial. So I folded that 5 factorial into this, right? So you get 7 times 6 times 5 factorial, and that's 7 factorial. And then with the numerator, again, with these, it doesn't look like we're really going to get anything useful. But then notice the even ones all have A0s in them, right? Even going back up to A2's got an A0 in it. The odd ones all have A1s in them. There's an A1, there's an A1, there's an A1. So what we could do is rewrite Y as, with all the A0s grouped together, everything with an A0 in it, then everything with an A1 in it all grouped together. Because then you could factor the A0 out. And you'd be left with 1 minus x squared minus 1/6 x to the 4th. I guess we might as well simplify these now, because it didn't look like there was much of a discernible pattern in the numerator. So I did just go ahead and rewrite that as 1/6. And then that one ends up being 7 over 90, if you factor a couple of things out. And then here, we can, out of this second set of brackets, we can factor out the A1, right? And then we've got x, and then 3 factorial 6. Here, this is 7 over 120. This actually simplifies a little bit, the 161 over 7 factorial. Looks like you can factor 7 out. But we end up here, and that is the thing that we were aiming for, where we've got 4 terms in Y1, 4 terms in Y2, and we've got the A0 and the A1 factored out. So there is a lot after the recurrence formula, actually, to get it all the way down where you've got it written in the form of A0 times something plus A1 times something else. The next example is a first order equation. So clearly you don't need to use a series to solve this. Right, just the way it's set up, it's kind of set up for an integrating factor. But you could do separation of variables too if you wanted. The point of doing this is to have one that's just a little less ugly, just so that way the steps are easier to see. But yeah, you wouldn't have to do it this way, and if it said solve this, and you could do it whichever way you wanted, you wouldn't pick series, I would imagine, unless you wanted it to be longer. And I don't think anybody wants that. So if we're going to use a series here, notice there's no y double prime. Right? Shouldn't be. It's first order. So you just need y and y prime. Don't need the y double prime this time. So then we sub in. So there's y prime plus 2x times y. And then I put that x into that sum. So that's why I have an x raised to the power of n minus 1 there. And then the first thing is to match exponents. I guess you have some different options here, but I just made both of them x to the n. Usually that's the simplest thing you can do. So then that means in the sum that's on the left, I've got to go up 1 on that n, and this n in the exponent, and then down 1 in the starting point. So starting point, now it's 0, and then n plus 1 there, n plus 1 there, and then n minus 1 plus 1, which is n right there. This one here, I need to get from x to the n plus 1 down to x to the n, so I got to go down 1 here and down 1 on this index, and then up 1 on the starting point. So starting point is now n equals 1. And then going down 1 here, we've got the n minus 1, and then down 1 up here, n. All right. Once those are lined up, Then we've got to line up the starting point, so you got to pick the later starting point. So we're going to start at 1, which means we got to pull the first term of this one off, since this one's starting at 0. So that's what I did here. I just pulled the first term of this off. When n is 0, you get a sub 1 times x to the 0. That's just a sub 1, right? And then the rest of that sum, we could start at 1, and then these two you could combine together, which is what happens on the next step. So a1 out there by itself plus the sum from n equals 1 to infinity of, then we're going to have this big coefficient multiplied by x to the n. So from the first sum, a sub n plus 1 times n plus 1. From the second sum, 2 times a sub n minus 1. So what are we getting? Well then, if this whole thing's got to be 0, then a1 has to be 0. And this coefficient's got to be 0, so a sub n plus 1 times n plus 1 plus 2 times a sub n minus 1 also got to be 0. But then this will give us the recurrence formula, so solve for the higher index again, so you want to solve for the a sub n plus 1, so that's what I did there. You end up here. All right, once you got the recurrence formula, with a1 being 0, this is a fantastic thing. Half of it is done, because look at how this is set up. The recurrence formula uses the term that's 2 before it, right? Just in terms of the indexing, n minus 1 comes 2 before n plus 1 does, right? So that means that the evens are all going to go together, right? That a sub 2 is going to be based on a sub 0, a sub 4 is going to be based on a sub 2, that kind of thing. And the odds are also going to go together. So like a3 is based on a0 and a5 is based on a3. Or a3 is based on a1, a5 is based on a3, that kind of thing. But a1 is 0. So if a1 is 0, looking at this, like if n is 2, that would give you a3, but then it would be negative 2 times a1 over 2 plus 1, but a1 is 0. So if a1 is 0, then a3 is 0. But then a5 is based on a3. So if a3 is 0, then a5 is 0, which then forces a7 to be 0, which forces a9 to be 0, and so forth. All the odd ones are going to be 0. So when you get this kind of situation where effectively one of those sequences is going to terminate, that's really nice. Cuts the work way down. But then we do have to do the even ones. So if n is 1, that'll give you an even. So it'll give you a sub 2. All right, so a sub 2 would be negative 2 times a sub 0 over 2. We can say, all right, for now I'll just call that negative a sub 0. If n is 3, that'll give us a sub 4. So it's negative 2a2 over 4, but a2 is negative a0, so I sub that in right here. So then that's negative 1/2 times negative a0, so it's just 1/2 times a0. All right. If n is 5, that'll give us a6, which is negative 2a4 over 6. But we said a4 was 1/2 a0, so I sub that in right here. So then we get negative 1/3 times 1/2 a0. And I'm writing it like this just to make the factorial more obvious. So I saw this and I went, okay, yeah, that is going to be negative 1/3 if you simplify it. But I can also rewrite this so there's a 3 multiplied by 2 in the denominator, right? And that's a 3 factorial. If n is 7, a8 would be negative 2a6 over 8, but a6 is this. So notice when I put that in there for a6, and then I say, wait a minute, this is 1/4, right? 2 over 8, so there's the 1/4. And negative times a negative will give you positive. So we're starting to see things, right? Because then you go, the signs are alternating, because that's negative, that's positive, that's negative, that's positive. And then you can see the factorial forming, because you go in the denominator from 2 to 3 times 2 to 4 times 3 times 2, right? So what are we getting? The a4 up here, it's 1 over 2 factorial times a0. a6 is negative 1 over 3 factorial times a0, right? That's what that is. a8 is 1 over 4 factorial times a0. So we're getting somewhere, right? So if you write that all together, we've got this. We've got a0 minus, and then a2 is just negative a0, right? Then a4 is right here, right? The 1 over 2 factorial a0. Here's the a6, the negative 1 over 3 factorial a0. Here's a8, or if you factor out the a0, this helps. Makes it easier to see what's happening. 1 minus x squared plus 1 over 2 factorial x to the 4th minus 1 over 3 factorial x to the 6th and so forth. I guess you could argue this one is 1 over 1 factorial right there, and I just didn't write it in. And then this 1 is 1 over 0 factorial. If you want to take it to that extreme and write it that way, you could. But then if you're going to write that as a sum, you could, right? It'd be the sum from n equals 0 to infinity. And this is the tough part, being able to write it in summation notation. So we said that the signs are alternating, right? And so then if you think of the indexes now as like there's been a reset, and instead of thinking of this as like index 0 and then 2 and then 4 and so forth, think of it as like this is 0, this is 1, this is 2, this is 3, this is 4. Like the most conventional thing you could have. Because then you could say, well, the way the sign alternates is it's negative 1 to the n, right? Because then 0, 2, 4 are all positive, and then 1, 3, 5, and so forth are all negative. So you get that negative 1 to the n, and then x would be raised to the power of 2n, right? If you think of this as like an index of 1, there's 2 times 1. This is index 2, this term, this is 2 times 2. This is index 3, this is 3 times 2, 4 times 2 up there, right? And then in the bottom you have n factorial, right? Because then you can argue there's a 0 factorial here and a 1 factorial here. Then you have the 2 factorial, the 3 factorial, the 4 factorial. Next term we have a 5 factorial, right? So it looks like this. This is tough to get it written as a sum. This is where you're really reaching deep into the Calc 2 bag of tricks. But that's kind of what you have to do in order to get it. The tough part, and this was what I always thought was the tough part, is when you get here to kind of reframe it in your brain to where it's index 0, 1, 2, 3, 4 instead of 0, 2, 4, 6, 8. Right? Because very suddenly that switches. But it's like once you've factored the A0 out, you just have to think that it's almost like there's a reset. And then it just goes back to the usual 0, 1, 2, 3, 4. But once you've got this, I mean, really that's it. But I did stick this extra thing in here because look at what we get. You could rewrite that numerator as negative 1 times x squared all raised to the nth power, but negative 1 times x squared is negative x squared, right? But you look at the sum, you go, wait, that's one of the greatest hits of the Maclaurin series. It's basically, it looks like e to the x, except that you have a negative x squared where the x goes, right? That means that this sum is e to the negative x squared. And that's exactly what you should get if you solve the equation that I guess was on the last page now, because it took 2 pages to get here. But y prime plus 2xy equals 0. If you solve that using an integrating factor or separation of variables, that's what your answer looks like, which is exactly what this is, right? Because that sum is e to the negative x squared, and then here the arbitrary constant is called a0. Here it's called c, but those are still just arbitrary constants, right? The a0 and the c are placeholders. So yeah, you get the same thing. It looks more complicated, but you do get what you're supposed to. So, all right, I guess it's good that you get what you're supposed to. I know this is much, much longer than using an integrating factor, but I did want to have one where it was a little bit simpler, just so that way the steps would be a little more concrete looking. And the individual parts looked a little less obscure. Example number 3, if you're eyeing this one up and thinking, couldn't you just do a substitution, say u is equal to y prime, and do it like that, like we would have done it toward the beginning of the course? You could, but this is another one where I think it's worth doing it with a series, and amazingly, this one fits on a single page. So, if we're going to do it with a series, so we're going to assume the usual form of the solution for y, some power series. We're going to need y prime and y double prime, so we're going to sub in y double prime and y prime right there. So then that's what we're going to do. Then the first thing is to match up the exponents. I made them both x to the n. You don't have to do that. I guess you could make them both x to the n minus 1 or something if you wanted to. But I just figured that would be the easiest thing for me to follow along with mentally. And I also went, ooh, wait, I'd have to subtract 1 there and subtract 2 there. So when I match up the exponents, I'm going to match up the starting points too. But I guess that would actually happen no matter what exponent you pick to match, that the starting points would sympathetically match in this particular case. But anyway, I did set it up so they were both going to be x to the n. So that meant here I had to go up 2 everywhere, right? Because I got to go from x to the n minus 2 to x to the n. So that means here I got to go to a to the n plus 2. N becomes n plus 2. N minus 1's got to become n plus 1. And then here I got to go down 2, right? Got to go the opposite way, so starting at n equals 0. Same thing here, but a difference of 1 instead of a difference of 2. Got to go up 1 here, so then up 1 here to a sub n plus 1, and then n to n plus 1, and then down 1 on the sum, or at least the starting point of the sum. All right, great. Well, since the starting points also match, we can go right ahead and combine this into one big coefficient of x to the n, and we don't have to pull anything off of any of the sums or anything, so that's nice. But then we know that this thing in brackets has got to be equal to 0, right? So that's the next thing. And then if we solve that for the higher index, so solve that for a sub n plus 2, you end up with that that's a sub n plus 1 over n plus 2, because those n plus 1s are going to cancel. Okay, that doesn't look so bad. Another thing that's noticeable here is the difference in indexes this time is only 1. And what that's going to do is that means that when we get our sum, it's, well, or at least when we get our solution, it's only going to have a single sum instead of 2 of them. But that's okay. Sometimes you get lucky, and that's what we're doing right now. All right, so now to get the first few terms to see what kind of pattern we got going on, well, if n is equal to 0, then that would tell us if we sub in that a sub 2 is equal to a sub 1 over 2, right, or 1/2 a sub 1. Then if n is 1, then a3 is going to be 1/3 a sub 2, but then a sub 2 is 1/2 a sub 1, so okay, 1/3 times 1/2 a sub 1. If n is 2, then a sub 4 is 1/4 a sub 3. Sub in this right here for a sub 3. So then a4 is going to be 1/4 times 1/3 times 1/2 times a sub 1. I think you can see the pattern here, but I threw in one more just for fun. If n is 3, then a5 is 1/5 a sub 4. Then a sub 4 is this right here. So you put that in there and you go, yep, I'm definitely seeing the factorials now. All right, so then what we're going to have, if I write this all out with the substitutions in there, so you have a0, right? That's still just there as a0, which notice that never comes up here, which factors in a minute. But you have a0 plus a1 times x, but then a2 was 1/2 a1, so there's the a2. a3, right, there's the substitution from right here. a4, there's the substitution from right there, and I was out of space, so I didn't put the a5. But then you could factor the a1 out of all these terms, so I did it. You've got x, 1/2 x squared, then 1 over 3 factorial x cubed, 1 over 4 factorial x to the 4th. You go, okay, the thing in brackets does not look like it's that crazy, right? You start at 1, and then you just have x to the n over n factorial. You could make that start at 0 if you really wanted to, but you don't have to. Right? Keep it simple, I think. But then why is this a0 just kind of hanging out here and this never showed up? Well, that just means that if you were going to have a fundamental set of solutions, one of them could be 1. Or really any constant. And that's okay. So every once in a great while, every once in a blue moon, you're going to get that. So really, if you look at this, the way that I've got this phrase is that even though this sum isn't starting at 0, it almost looks like what the answers would be e to the x and 1. That would be a fundamental set of solutions. If you go up toward the top, like just looking at the differential equation, you go, well, yeah, right? With e to the x, the first and second derivatives are both e to the x, so yeah, that works. And for any constant, so I guess 1 to keep things simple, the first and second derivatives are both 0, so yeah, this works. So just kind of eyeballing this thing, you would think, yeah, the things that should be the answer are constants and e to the x, multiplied by some arbitrary constant. And that's exactly what the answer is. It's phrased a little bit differently. If you want to get it to where this is really e to the x, you can rewrite it. And that's basically what I did here is I added in an a1 into here. And so that's why it's subtracted out there. And then you could fold this together and say, well, that's the difference of two arbitrary constants. So I just rewrote that as a2 as a third arbitrary constant. Plus a1 times, now this is e to the x because it's starting at 0. And so, yeah, that's what we've got, right? 1 and e to the x would be a fundamental set of solutions here. But this was another one where you don't really have to do it with series, but I figured it was worth it because this is another one where we can figure out the pattern pretty quickly with the factorials. So if nothing else, it was to get used to that, to seeing the factorials. The last example, example 4, as opposed to the last couple, this is one where you kind of do have to do it with a series. You can usually tell the ones where you have to use a series because the answers look a little wild. And this one, that looks pretty wild, right? I mean, just looking at this thing, you go, how are we ever going to end up there? Well, we are. This, I think, is the high end in terms of difficulty and what we're going to do with series solutions, especially to try to get this piece, because that's hard to see. But that's what we're going to do. All right, so we've got first and second derivatives, so we're going to need the first and second derivatives here. And then subbing into the differential equation, there's y double prime, there's y prime, there's y. Then what I'm going to do is I'm going to put that x in here, right? So then that's why down this line I have a sub n times n x to the n, because I put that x inside the sum. Then the first thing is match up the exponents. Okay, well, we've got a couple that are ready to go, where this is x to the n, this is x to the n. Here's an x to the n minus 2, so that's one we got to line up, right? We're going to want an x to the n here, so it's going to be up 2 on everything here, all right, all these n's, and then down 2 on the sum. All right, well then if we do that, there's the x to the n, so a sub n now is a sub n plus 2, n to n plus 2, n minus 1 to n plus 1, and then down 2 here, so we're starting at 0. Then after that, we got to match the starting points. So 0, 1, 0. We're going to have to start the sums at 1, which means we got to pull off the first term on the one on the left, pull off the first term on the one on the right. And that's what this is down here. When n equals 0, here, if n equals 0, you're going to get 2 times a sub 2. Here, if n equals 0, you're going to get 2 times a sub 0. So I put those out front, and then I said, well, we could start the sums all at 1 now, and so then that means we can combine them together, and we have this giant coefficient for x to the n, and it would be what you get from the first sum, which is all this, and then the second sum is the minus a sub n times n, and the third sum is the 2 times a sub n. Okay, then that would mean that this constant out here, because that's really what this is, right? It's just some constant term that's got to be 0. So a2 got to be negative a0 for that to work. Then this coefficient here has also got to be 0. So let's see. I combined terms here because I have the two a sub n terms, and I just said, okay, plus 2 minus n times a sub n. And then you want to solve for the higher index, which is a sub n plus 2. All right, so I guess when I did the solving, since I had to subtract, then rather than having a minus sign out here, I distributed it, so n minus 2 instead of 2 minus n. That's why that flips around, right? Because it's multiplied by negative 1. And then that's right there inside the red box. That's the recurrence formula. All right, so then using it, I did the evens first. So if n is 0, then that would tell you that a2 is going to be negative 2 times a0 over 2 times 1, which is 2. All right, so a2 is negative a0. But then if you go to n equals 2, look at this. a4 is going to be 2 minus 2 times a2 over 4 times 3. The 2 minus 2 is the important part, because that's a 0. And then you go, well, the way that this is set up, if I scroll back up to it for a second, right, there's a difference of 2 between the indexes. So that means if a4 is 0, a6 is going to be forced to be 0, right? Because it's going to be n minus 2 times a4 over this, but that's a 0. So a6 is 0, but if a6 is 0, then a8 is 0, and so forth. So for the evens, really we're just going to have an a0 and an a2. And then everything after that's 0. Okay. Then for the odds do not have anything like that, but at least there is a nice regular pattern here. So for the odds, a3 ends up being 1 minus 2 times a1 over 3 times 2. And if you're kind of eyeballing that and going, 3 times 2 looks like a 3 factorial. That's what I would be thinking too. Then if n is 3, then a5 would be 3 minus 2 times a3 over 5 times 4. So I said, all right, well then that's 1 over 5 times 4 times a3, but a3 was this. So 5 times 4 times 3 factorial gives you that 5 factorial there. And then the minus 1 times 1 gives you the minus 1, and then a1. If n is 5, then a7 would be this. So 5 minus 2 times a5 over 7 times 6. And then if you sub in a5, so this right here, we're going to get a 7 times 6 times 5 factorial, which is 7 factorial on the bottom. Then we've got 3 times 1 times negative 1. All right. And then with the a1 out there. And then when n is 7, so a9, we end up here just subbing in. But then if you sub in this expression here for a7, then you'll get 9 times 8 times 7 factorial, which is 9 factorial on the bottom. And then 5 times 3 times 1 times negative 1 in the numerator times a1. So you can see how it works, right? N sub 9 is going to have an 11 factorial on the bottom. And then on, right, like, or if n equals 9, you're going to have a sub 11. That's going to have an 11 factorial on the bottom. You have 7 times 5 times 3 times 1 times negative 1, right? Like, you can see what's coming now. So I think we got the pattern down. All right, so a1, y2, right? So there's a1, there's a3, there's a5, there's a7, right? There's a9. We can factor the a1 out, and we're going to end up with this. Okay, well, then I can see how you write the factorial, but what do you do with the rest of this? The most common way of writing this is actually not to include the negative 1. So how it's just kind of factored out here. And you don't actually have to do it this way. Like there are other ways that you can write it, but this would be the most conventional, even though it doesn't necessarily look it. But what I ended up doing is where I have this multiplier here, where it's 1 times 3 times 5 up to 2n minus 3. Where the 2n minus 3 is coming from, it's if you think of like if there's going to be that reset again, where then that's index 0, that's 1, that's 2, that's 3, that's 4. Right, then that's essentially what we're getting at. So like if this is 4, then 2 times 4 minus 3 is 5, and that's what we're starting. Well, I guess here it's going in decreasing order instead of increasing order. That's why we've got the 5 in that one. That's the biggest thing. Right here, if it's 3, 2 times 3 minus 3 is 3. Yeah, that's the biggest one there. Here, it's 2. So 2 times 2 minus 3 is 1. Right, that's the biggest one there. Then, let's see, other than that, let's see, this one actually kind of fits in with this if you start with the negative 1 instead, and you wanted to stick that in there. But we'd end up with, so 3, I guess it's hard to see it from here with index 0, like how you get to the 1, but you have 0 getting mapped to 1, 1 to 3, 2 to 5, 3 to 7, 4 to 9. So it's 2n plus 1. And that's one where even if you just have to write it as like, okay, 0 mapped to 1, 1 mapped to 3, 2 mapped to 5. That's, I mean, if I don't see it, that's what I start doing if I don't see it right away. And then it's the same number in the factorial, right? Exponent and factorial are matching up, so 2n plus 1 factorial down there. And this is starting at index 2. So this is one way that you can write it, and you could also fold this index 1 term back into the sum if you wanted to, and then you're just starting this multiplier with a negative 1, and that's fine. So there are a couple of different ways to write that one, but then the other part, the a0, y1, because remember, it was only a0 and a2 that aren't 0. So a2 is negative a0, so you get a0 minus a0 times x squared. You could factor an a0 out of that, and you're left with 1 minus x squared. So then there's that part for the evens, and then the part for the odds is that, and then I just rewrote 3 factorial as 6, and you end up there. So this one, I wouldn't give you one like this on a test, just because this thing in particular out here is a little bit weird, but I think it's worth going through, because then if you can see this pattern, which is one that's a little unconventional, then the conventional ones feel a little bit easier. But yeah, this is about the high end of what you end up doing with series solutions, at least second order series solutions. I don't think you'd see anything wilder than this.